Hi, this is Dr. Bricker here with some hints for homework number 10. The first one, the wave speed on a string under tension is 210 meters per second, and you can review these pages. What is the speed if the tension is doubled? So we need to know the relationship between speed and tension. Let's take a look at it. So the key idea here is, here's the speed. It's equal to the tension, and I'm calling tension F sub t to distinguish it from t, which is used for period. Sometimes you see period, sometimes you see tension in these problems. So just to be clear, this is the tension divided by the mass per length of the string. And the mass per length of the string is literally the mass of the string divided by the length of the string. So a thicker string will have waves travel with a slower speed, as you can see here. So the speed is proportional to, that's what this symbol means, the tension. And again, I'm told the speed is 210 for a given tension. What is the new speed if we double the tension? So you might try to guess, well, if you double the tension, you double the speed. But that's not how it works out. The speed is proportional to the tension. So I don't know what the tension is. I don't know what the mass per length is. I just know that they're the same. Mass per length, tension is going to be different. This allows me, though, to set up a ratio. So old speed is to new speed, and again it's a square root relationship, as the square root of the original tension is to twice the tension. And now it's an actual equation. So do a little bit of algebra. You'll see that the new speed is equal to the old speed times this. The square root of the new tension, which is twice the old, times the old. And then the old actually cancels out. And you get original speed times the square root of 2. So it doesn't double, it increases by a factor of the square root of 2. Next one, early test of sound propagation through ocean. An underwater explosion of 1 pound of dynamite in the Bahamas was detected 3,200 kilometers away on the coast of Africa. How much time elapsed between the explosion and the detection? And we want the time in minutes. Okay, so if you look up under constants, the speed of sound in salt water, you know the speed, you know the distance here, you can figure out the time. Let's take a look at it. So if you did look it up, you'd see that the speed is 1,500 meters per second in salt water. The distance is 3,200 kilometers, so kilometers means times 10 to the third, which then would be 3,200,000 meters, or if you want, put it into scientific notation. And this still holds. The speed is the distance divided by the time. A little bit of algebra, time, distance over speed. Distance is given. You looked up the speed, you could figure out the time. Now this will come out in seconds. You'll just have to turn it into meters. Next we have a 2-meter long string fixed at both ends, as you can see in the picture here. 2 meters long, tightened till the speed is 40 meters per second. So the tighter you make it, the faster the speed will be. And we want to know what is the frequency of the standing wave shown in hertz. Okay, so 2 meters long. That does not mean that's the wavelength of the wave. We have to count the amount of antinodes to figure out the mode that we're in, and then once we have the mode, we can figure out the wavelength. So count the high spots. These are the antinodes. 1, 2, 3, 4, 5, 6. So this is the 6th harmonic. Okay, let's put all this information together. Okay, so length of the string, 2 meters long, speed 40 meters per second. What is the frequency? So I counted the amount of antinodes to get the harmonic that I'm in, 6th harmonic. So the wavelength is 2L divided by N. So the wavelength is actually, if you put the numbers in, 2/3 of a meter. So the speed is related to the frequency and the wavelength through this relationship. Frequency times wavelength is equal to the speed. If you think about it, here's a wave. You know, however many, I'll just make it up to here. That'll be better. A traveling wave, this is the period. This is one wavelength. The speed is the distance that you travel divided by the period, or using that the frequency is 1 over the period, you get that relationship. Okay, so speed, frequency times wavelength. We're looking for the frequency. It's the speed divided by the wavelength. So the speed's actually given. You have to do a little bit of work to get the wavelength and then put it all together. Okay, next one, bass guitar string, 89 centimeters long, so that would be 0.89 meters, with a fundamental frequency of 30 hertz. What is the wave speed on the string? Okay, so fundamental frequency means n is equal to 1. Okay, let's put this all together. Okay, so the length of the string is 0.89 meters. Fundamental frequency, 30 hertz. Again, that means n is equal to 1. The length is 0.89 meters. That doesn't mean the wavelength is 9 meters. The wavelength is 2L divided by n, just like we saw before. So the wavelength here is actually 2L divided by 1, because when they say it's the fundamental frequency, that means n is equal to 1. And then the speed, frequency times wavelength, we can solve for the speed. Okay, 16-17 rather. The lowest note on a grand piano has the frequency of 27.5 hertz, so the very lowest frequency. The entire string is 2 meters long and has a mass of 400 grams, so divide that by 1,000.4 kilograms. The vibrating section of the string is 1.9 meters long. What tension is needed to tune the string properly to have this frequency? Okay, let's take a look at it. Okay, so the frequency is 27.5 hertz. I know that's the fundamental frequency because that's the lowest frequency. The actual length of the string is 2 meters long, and the mass is 400 grams. So again, divide it by 1,000.4 kilograms. So I can use this to get the mass per length because they give me the mass and they give me the length. The part of the string that's actually vibrating is 1.9 meters long, so those are the endpoints. And we want to know what is the tension. So the mastering physics has T for tension. Again, I'm using F sub T for tension. So the speed we've seen is the frequency times the wavelength. The speed is also the square root of the tension divided by the mass per length. It's the same speed, so those are actually equal to each other as well. The square root of tension over mass per length is equal to the frequency times the wavelength. And again, we're trying to figure out the tension. So this is equal to this. Square this, square this. You get tension over mass per length is frequency squared times the wavelength squared. One step of algebra, tension, mass per length, frequency squared times the wavelength squared. Okay, so you had to do a little bit of work here to get the mass per length, but it's doable. The frequency is actually given. Now the wavelength, just like we had before, 2L over n. Here, though, I distinguished L from L prime. The wavelength is the actual part where the wave is contained. So just to be clear, I called it L prime here. And then divided by n. And again, they say it's the lowest frequency, so we know it's got to be the fundamental frequency. And then you can get the wavelength that way. So lots of little parts to put together. Specifically, you have to calculate mu, you have to calculate the wavelength, and then put it all together to get the tension. Next one, it's a guitar string. Mu is actually given in this problem, 2 grams per meter. Just be careful. That's you need it to be in kilograms per meter, so divide that number by 1,000. It's stretched between supports that are 60 centimeters apart, so 0.6 meters. The string is observed to form a standing wave with 3 antinodes. So 3 antinodes means it's the third harmonic, n is equal to 3. Driven with the frequency of 420 hertz. Okay, so F sub 3 is 420 hertz. We want to figure out in part A, what is the frequency of the 5th harmonic? And then in part B, what is the tension in the string? Okay, so we're putting all the standing wave concepts together in this problem. Okay, mu is given 2 grams per meter. That would be 2 times 10 to the third. 2 times 10 to the minus third, rather, kilograms per meter. They tell us 3 antinodes, so that tells us that n is equal to 3, and that corresponds to 420 hertz. We want to figure out, given the length of 0.6 meters, what is the 5th harmonic, and then what is the tension. Okay, so we can get the 1st harmonic because the fundamental frequency, or 1st harmonic, the other frequencies are just multiples of the fundamental frequency. So once we get the fundamental frequency, we can figure out any frequency we want. So the 3rd harmonic is n times the 1st harmonic. So a little bit of algebra, divide both sides by n. This third harmonic frequency divided by 3 will give you the fundamental. So 140, F2 would be 280, F3, as you can see here, is 420, and right on down the line, then you can get the fifth harmonic that way. So they're always just multiples of the fundamental. So get the fundamental, which we did, which is 140, multiply it by 5 to get the fifth harmonic. Okay, and then to get the tension, we can use what we did in the last problem. Actually, it's right here. Mu times the frequency squared times the wavelength squared will give me the tension. So the tension, mu, pick whatever frequency and corresponding wavelength that you want. We've already got the fundamental frequency of 140. We could use this corresponding wavelength, which would be 2L over 1, when n is equal to 1, and that could be the wavelength. You could very easily have used F3 and wavelength 3, and you would get the same tension. Okay, excellent. Okay, the next one, we're switching into fluids. The deepest part in the ocean is 11 kilometers below sea level. Deeper than Mount Everest is tall, and you can review these pages, 401 to 404. What is the pressure in atmospheres at this depth? So we want the answer in atmospheres, which is not an SI unit, but we can convert it to atmospheres. Okay, let's take a look at this. So the idea here is the pressure at depth, so P1 is equal to the pressure at top, which I'm just calling P0, you can call these things whatever you want, plus rho g times h. And the rho that I'm talking about here is the density of the fluid. So imagine you're in a submarine or something going into the ocean. The pressure keeps getting greater and greater and greater because you have this whole column of fluid above you. So pressure at depth is pressure at the top plus rho gy. And if it's open to the atmosphere, it's atmospheric pressure, which is 1.013 times 10 to the 5th pascals. So a pascal is a Newton per square meter. So this is an SI unit here. Okay, and we're trying to figure out the pressure at depth. So we're trying to figure out pressure 1. And the h here, the height, is 11 kilometers, so 11 times 10 to the 3rd. So pressure at depth is pressure at the top plus rho g times h. So I looked up the density of salt water, 1,030 kilograms per cubic meter times 9.8 times 11 kilometers. Okay. You'll notice that we have a kilogram meter per second squared, which is a Newton, and then one of these cubic meters cancels with this cubic meter, so we're left with newtons per square meter, which is a pascal. So when you do this, the answer comes out in pascals, and then you have to convert it back to atmospheres with this conversion factor. 1 atmosphere, 1.013 times 10 to the 5th pascals. Next one, similar to what we just did, 0.6 meter diameter vat of liquid, which we don't know what the liquid is 2.2 meters deep. So we're going to have to assume that this vat is in the shape of a cylinder. The pressure at the bottom of the vat is 1.3 atmospheres. So not an SI unit, but we can still work with it. What is the mass of the liquid in the vat? Okay, so it's a pressure at depth problem. We just have to kind of work it backwards a little bit. Let's take a look at it. Okay, so I've drawn my vat here, and it's filled with the liquid. The depth of this vat is 2.2 meters. Now it's open to the atmosphere, so at the top we have atmospheric pressure here. The pressure at the bottom we're given to be 1.3 atmospheres. Perfectly good unit, just not an SI unit, so you can convert that to pascals. Okay, so we're also given the diameter of the vat, 0.6 meters, so half of that would give us the radius, which is 0.3 meters. The reason I'm doing this is if I know the pressure at the top and the pressure at the bottom and the depth here, I could figure out the density of this fluid. And then once I know the density of the fluid, I can figure out the mass because I can calculate the volume. So the volume is pi r squared times d. That's the volume of a cylinder. Okay, so I'll recap this, but let's follow along. Pressure at the bottom is equal to pressure at the top plus rho g times the depth, which I call d here. A little bit of algebra. Pressure at bottom minus pressure at top divided by g times d gives me the density. And I'm really looking for the mass though. So if I use this relationship, the density is the mass over volume. Density times volume gives me the mass. And then I can calculate the mass. Good, so I've used the pressure at depth idea to get the density here. And just from the dimensions of the vat, I get the volume. And then once I have both of those, I can get the mass, because density times volume gives me mass. Okay, so here I have a gas in this container. And we've got mercury in this tube, which is open to the atmosphere. So if the pressure in the gas gets greater and greater and greater, you could imagine this column height shifting this way and this way and this way. When the height over here and the height over here are the same, then the gas is at atmospheric pressure. So the way it is now, the atmosphere is pushing down more than the gas. So the gas pressure here is actually less than atmospheric pressure. Okay, so they tell us the fluid is mercury. We actually know more than we think we know. It's mercury, so we can look up the density of mercury. And we have these different dimensions. We can figure out the pressure in this device. Okay, so I've reproduced the drawing here. Here's the gas. Here's mercury in the tube. Again, the gas pressure is going to be less than the atmospheric pressure because the tube is lower here than it is over here. So the pressure at this level would be the gas pressure. Here, P1, I'm just calling it P1, you can call it whatever you want. This is open to the atmosphere, so this is atmospheric pressure. Okay, and it's mercury. I know the density of mercury, look up in the chapter, 13,600. Atmospheric pressure, again, 1.013 times 10 to the 5th pascals. And this is 6 centimeters here. They told us this whole thing was 16 centimeters. So this ends up being 10 centimeters here. Okay, very good. So looking back at the left-hand side here, the pressure at this depth is equal to the pressure at the top. And the pressure at the top is because of the gas times rho gy. So just like we did before, the pressure here is because of the pressure at the top plus rho gy, the height of the fluid. Okay. So let's use that formula. P1 is equal to the pressure of the gas, and again that's the pressure at the top, plus rho gy, and y here is 10 centimeters. So we're looking for the pressure of the gas, a little bit of algebra, pressure at the bottom minus rho gy. Again, I just did a little bit of algebra to get the pressure of the gas. Okay, good. So density of the fluid, G, and then y here is the height of the fluid. Be careful, make sure you put that into meters. Okay, 13-20, again you can review these pages, which we actually will take a look at in just a minute. What is the height of a barometer at atmospheric pressure? Suppose that the barometer was made using oil, density of 900 kilograms per cubic meter. So usually these kind of barometers are made with using mercury. Mercury is a lot denser than this oil. The height of the column of fluid for mercury is a lot less than would be using this oil. Here's the idea. You take this test tube, fill it with the fluid, dip it in this tray, turn it upside down, and you get this picture. And there's no pressure up here because this is not open to the atmosphere anymore. This is atmospheric pressure here pushing down. P1 and P2 are at the same height, so they have equal pressures. So if you did this, all of the fluid's not going to leak out of the test tube. It's going to stay like this because atmospheric pressure is pushing down. And we want to figure out what atmospheric pressure is. So you actually do this, you measure the height, you can figure out atmospheric pressure. Let's take a look at it. So I've taken my test tube, just like in the previous picture, put it in the liquid, turned it upside down. The pressure up here is 0 because it's not open to the atmosphere anymore, it's a vacuum. P1 here is open to the atmosphere, so it's just atmospheric pressure. P2 here is equal to the pressure at the top, which is 0, plus rho gy, the height of the column of fluid here. So again, P1, atmospheric pressure, P2 would be equal to whatever is at the top, which it turns out to be 0, plus rho gy. These are at the same height, so they have the same pressure. P1 is equal to P2. We're really trying to figure out P1, which is atmospheric pressure. So P1 then, rho gy, y is the height of the fluid. Height of the fluid here. And then you can, do a little bit of algebra, solve for the height here. So don't be surprised if you get a pretty large height compared to, say, if you used mercury, you would get something like 760 millimeters of mercury. This height's going to be a lot greater. Might be like a 2-story building if you tried to make a barometer out of oil, or even greater than 2 stories. Okay, a 6 centimeter diameter sphere, and the mass is given, 89.3 grams, is neutrally buoyant in a liquid. So neutrally buoyant means all the forces up, which is the buoyant force in this case, are equal to all the forces down, which is equal to mg. So for something to be neutrally buoyant, the density of the object is equal to the density of the fluid. So whatever this is submerged in, if it's neutrally buoyant, it has the same density as the fluid. So if you can figure out the density of this object, it's equal to the density of the fluid. And then you can identify the liquid. So the mass here, make sure you put it in the kilograms. The diameter of a sphere. You'll have to remember what the volume of a sphere is. It's 4/3 pi r cubed. So take the mass in kilograms divided by the volume in cubic meters. You'll get the density of this sphere that's equal to the density of the fluid. And then the last step here is look up in the chapter whatever density you get, compare it to the table of known densities to figure out what liquid you have. Okay, let's take a look at the last one here. We have this block of aluminum. We know the volume of it. The density is given. We want to know what is the tension in this cord. So if you submerge this aluminum in some fluid, the tension is less than if it's just hanging in air. Okay, so let's take a look at the final problem. Okay, so here's the free body diagram. Buoyant force is up, tension is up, weight is down, and we're trying to figure out the tension. So the density of aluminum is given, 2,700 kilograms per cubic meter. The volume is also given, but it's not in SI units. It's 100 cubic centimeters. So to make it into cubic meters, you've got to divide by 100 3 times. So it's 100 centimeters, 100 centimeters, 100 centimeters is 1 cubic meter. So take this, divide it by 100 3 times, and then you have it in cubic meters. The reason I want to do this, and you'll see in just a second, is I need the volume in cubic meters because it's SI units. The reason you need the volume is this. Tension is up, buoyant force is up. It's equal to mg, which is down. So tension then, doing a little bit of algebra, would be mg minus the buoyant force. So mg, it's the density of the object times the volume of the object. That's the mass of the object times g. Good, so I know the density of the object. That's really what this is. I know the volume of the object. That's really what this is. Times g. That gives me mg. And then the buoyant force is the density of the fluid, volume of the fluid, times g. Well, if it's completely submerged, the volume of the object is equal to the volume of the fluid displaced. So if you put 100 cubic centimeters in the water level changes by 100 cubic centimeters. Okay, so you know, a little bit of work to get the volume of the object, but you can do that. The density of the fluid you'll have to look up in a table. They tell you what the fluid's made out of. Look it up in the chapter and see what the density of that fluid is. The volume of the fluid is the same as the volume of the object because it's completely submerged. And then you have G again. Okay, so that's the final problem. Email me if you have any questions, and I'll talk to you soon.